Started recording, and first of all, I would like to provide you with a very important piece of information. You know, it takes time to schedule term tests. They are not going to take place during standard class time on various reasons. And we were fortunate that we got Wednesday, October 26, from 5 to 6 p.m. in two rooms, SW309 and SW319. I will not be late because I will be teaching at SW319 till 4:50. So I will not need to go far. Okay? So moreover, there will be TA office hours. Don't run mic, please. If you sleep, I'm in trouble, okay? Haste makes waste. Slowly, okay? So is it clear? So of course, we have some word to say about it, but I'm actually very happy with C62 test. Like there is a date for second test, but it actually overlaps with my B52 term test too. So I don't know if there will be some changes made for second test. But for now, this is the tentative information, but the odds for it to change are very low, okay? So that's what I believe will go forward. So, and of course, more details will be provided in the due course, okay? So now, I realize that it was rather hard stuff considered at the beginning of this course, but that's what I was requested to start this course from. Today, I'm going to continue with hope to finish the discussion of probabilistic measure theory today, but perhaps we'll still need to defer some topics till next Monday class meeting. But I also would like to build bridges today with the stuff considered in the first lecture. And I know you're still working on homework problems assigned at the end of lecture 1. I see some desperate Piazza posts which made up to my junk mail account. I don't know how, but I found it there this morning. When will solutions be posted? So read course syllabus. They will be posted eventually. Okay? Just find answers to your questions in the information that is already on Quercus. So you still have time to work on these problems and go. Yeah, so can you wave your hand, please? Yeah, go. You are go, yeah? Yeah, wave your hand, yeah? So what actually he knows were some stuff on lecture 1. Assignment number 1 is given in my UTM videos. So it's fall 2020, lecture 11. Yes, so ask him. So he will direct you what to watch, okay? And I'm still working on placing the link to my UTM videos on Quercus. So Aliya, who is helping us with videography, our Wednesday class meetings, actually, she takes B52, she watches these videos. So we are trying to make Quercus team do something. For now, I just forward the link to these videos. So if you already have this link, forward it to your peers who want them, okay? Now, I want to remind you an important formula considered at the very end of lecture 4. And this is going to be our starting point today, and I will also discuss it closer to the end of today's class meeting. Okay, so we have our probability triple, which we denote by S script F and P. So it induces a probability measure on R1, which is by capital P superscript X or capital P superscript X in parentheses. So this is the distribution of random variable capital X, which is a function from S to R1, or its subset. And you already learned on Monday that this is a measurable function. Yes, so, but the concept of measurability is to be discussed today. But I spoke about it before. Yes, so namely for any nice or actually Borel set capital B that belongs to a real line, we should have that the probability measure of the set which is induced by random variable X is by definition the probability of those elementary outcomes omega from our sample space S, for which the value of the function or our random variable for this elementary outcome belongs to this Borel set B on the real line. So that's what is denoted by probability that random variable belongs to the set, and it's denoted by x negative 1 of B. And I remind some Piazza questions on whether this is a one-to-one function. No, it is not. It's just a set. So x negative 1 of b, this is a, so it's a set or event from script f from the original sigma field script f such that for each omega from this set x negative 1 of b that belongs to this sigma field script f, x of omega belongs to this Borel set B from the real line. So the concept of Borel set is still to be defined. Okay? And these formulas, which I actually reminded, so you should have access to this formula in lecture 4 video and also in my lecture 4 notes. So this is basically the formula which I wrote in silence when we were to commemorate Queen Elizabeth II at around 1 p.m. Okay? So, but you saw this formula. I'm going to keep it on the chalkboard for the whole duration of today's lecture. I am not going to erase it and return to it closer to the end. So now I want to erase this stuff about term test 1. Yes, so of course it will be posted along with the remaining lecture notes of today. Okay? And the other thing, I'm getting questions about when I'm going to post lecture notes, etc. So when I'm going to post that, and that. So keep in mind that my posts is a courtesy of instructor. You should not consider everything that is to be given to you for granted. Okay? First of all, once, and I hope you all hear me, once you are assigned homework, you are expected to be completely responsible for it, period. So when I'll eventually post solutions or comments to solutions, it's something I do to help you with the studies, but it's not a part of something that I'm mandated to do. Is this clear? Okay? I repeat. And I, not here, but in the United States, I think for about, like it was for more than a decade, I chaired grievance committee where such issues came up. So students are completely responsible for the homework assigned. So you should make an effort. That is what is stressed out in the course syllabus. The other thing, my lecture notes. So they are kind of readable, but some words are being crossed. Few comments are being added, as you all noticed. So they're not typed as compared to my B52 notes, which is basically a revision of my UTM notes. I taught probability with measure theory flavor, or I would say I taught measure theory with probability theory flavor to make it easy for students digest abstract concepts. But it has been a while. I did it when I lived in Western Canada. And I taught similar stuff in Japan, but it also has been a while. Yeah? So therefore, this the notes in progress, which I improve, adding few comments and sometimes even few pages to make it more relevant for my students. Is it clear? Therefore, you are expected to be patient and considerate, and certainly you are welcome to make your own notes or watch the videos not just once, but for several times. Okay? Keep in mind that I do recognize that there is a huge conceptual gap between B52 level course and C62. I do realize that, as I said, I taught in 4 different countries, and I had students from all over the world. Okay? I traveled all over the world, but I gave research presentations in many countries. I didn't teach in more than 4 countries, but even that is enough, I would say. Yeah, and I do recognize also that many of you took B52 during the pandemic, so which is certainly it was a very stressful time. So I taught STAT 256 during pandemic online asynchronously at UTM for a very similar group of students, with the majority being computer science majors. You, of course, most of you are in stats and math, of course, yeah. But still, it was a challenge to teach and to study during the pandemic. Hence, I do recognize that it is important to connect some concepts from B52 and their more advanced versions considered in C62. Okay? But you are expected to make an effort, be patient, and not to expect everything being given to you on a silver platter. Okay? Not only for my course, for every other course which you take. And I do make effort to present this challenging stuff of measure theory introduction to probability in easy to digest terms. I certainly do have access to Professor Evans' notes from last fall, which are very rigorous, but they might not be too simple to follow, like you need to rederive each formula. So what I try to do is providing you some motivation, some intuition, and what is behind various concepts of this challenging part of probability theory. Okay? So, and you would need to work quite hard to recover the rest considered in other textbooks, like, like Billingsley's book. You are welcome to use notes of other instructors. Professor Evans' notes are great. I actually do have access to his last fall videos, which I may not share with you, though. Okay? But I also should say that if you look at other profs' notes on a similar stuff, it's also useful. Yeah, one of you showed me the notes of Professor Chow from California, so which he was reading. So you're welcome to look for additional sources of information on this stuff. Okay? And of course, if you're behind on B52 stuff, you're welcome to watch my UTM videos, but there are two elementary questions on that. Okay. So what I now want to do is really comment on this new probability triple. Because I said that we get a new probability measure on the real line, yeah? But we are to describe it. Hence, we are to provide the whole probability triple. We have the sample space, which is a real line. We got probability measure, which is defined along these lines. Yeah? So for certain set or certain nice event, or I would say, so it's Borel set or event, yeah, because it's probability theory, everything is rebranded. So we got a number. Hence, what remains is to describe this sigma field, or Borel sigma field, or Borel sigma algebra. Okay? But we still need to do it in order to completely characterize this new probability space induced by our random variable capital X. And I hope that you remember that for a single random variable, we can have numerous probability measures. It's not unique. Is this clear? Okay. Okay. So we have probability triple. On R1. So we have R1, the probability measure Px, and what we hear already. So we have script B, which is Borel sigma field on R1. So that's what we will consider in few minutes. But I also want to illustrate this concept with a useful example and also introduce new terminology. So the goal is to to continue example 2 from previous lecture. But I want to define the so-called indicator function of set or event capital A. So it's sig1 sub A of x, which is sometimes defined as chi sub A of x so it's just a different notation, which is 1 if x belongs to A, or 0 if x does not belong to this event A. So actually, the indicator function is a random variable. And in fact, it can be shown that any random variable can be represented as a sequence of linear combinations of indicator function of different sets. Okay? So indicator functions are actually building blocks for random variables. Okay? So, and in example 2, we consider the model of two tosses of a fair coin. Yeah? So, and in this case, the induced probability measure on a real line is as follows. So it's the number of points I and j, or it's a pair of two indices I and j, such that the indicator of event that I is h, or it's actually i's toss is h, plus the indicator of j's toss resulting in h belongs to b divided by 4, and we divide by 4 because it's a discrete uniform probability model. So, and let's talk on what we get for 3 values from the range of our random variable, which is the sum of heads. Okay, so we look at the number of heads in 2 tosses of a fair coin. Okay, so p superscript x of 2 equals the probability of those elementary outcomes omega, for which x of omega is 2. So that's what I'm rewriting, but in detail. So this is probability that x equals 2. That's what is written here. And we only have one elementary outcome, HH, which results in the sum or the total number of heads equal to 2, and its weight is 1/4. So this is simple. And I want to move on. Okay? Yeah?
Could you just say how that relates to the x minus 1 formula?
Of course. So x negative 1 of b is the set of those omegas from the sample space for which the total number of heads is 2. And this is actually what it is. So there is just a single omega HH from our sample space. Is that clear? So I can even write it's a single omega from the sample space S. Okay? So, and now I really need to move forward. So I know some took photos, but you, Aliyah, actually makes sure the whole chalkboard is recorded. You, of course, can always take screenshots, and Shaplots actually saw how she is uploading this video. Actually, she usually does it at the evening or at the end of the day when the lecture was held, okay? So around 5 o'clock, I think it will be available. And notes will take longer to be posted, okay? So now, yeah. Yeah. Yeah, indicator function will come up later on, Mike. So you'll see it. You will not be able to forget it. So also keep in mind that linear combinations of indicator functions are the building blocks for random variables. Okay? And also keep in mind that I'm already slowing down. I'm about 1 hour behind my schedule, okay? So it's actually great that I use chalkboard rather than the slides, but it certainly slows me down. So I don't mind, but I really cannot stuck on a simple concept forever. There's the whole syllabus I'm supposed to cover, yeah? So Px of 1. So here it's probability that x is 1. And this is the probability weight of 2 elementary outcomes, HT and TH. So this omega 1 and omega 2 from our sample space, and the probability is clearly 1/2. So probability P superscript x of 0 is probability that random variable x is 0. So, and this is probability of a single sample point TT, which is your only omega here, and this probability is 1/4. Of course, if we have other assumptions about the odds of head and tail, these probabilities are going to be different, but the random variable will remain the same. Okay, and we can consider something like that. We consider the closed interval from -1/2 to 3/2. So therefore here we need to take into account all elementary outcomes omega from our sample space. such that x of omega belongs to the interval from negative 1/2 to 3/2, which is written as probability that x is between negative 1/2 and positive 3/2. Clearly, it's probability that x is 0 or 1. I do it the long way, okay? But you should be able later to skip some steps and just connecting the original probability measure with the induced probability measure. So, and for this guy, we got 3 elementary outcomes for which the total number of heads is between negative 1/2 and 3/2. So TT, HT, and TH, which are omega 1, omega 2, and omega 3. And the weight is clearly 3/4. Okay? Again, it's not a rocket science. It's a simple example. So this is really a continuation of the second example from 4th lecture. Now I want to consider a somewhat relevant example, so which I call example 1 of today's lecture. So I roll a balanced die. So therefore, my sample space S is comprised of 6 elementary outcomes, 1, 2, 3, 4, 5, and 6. My sigma field script F is the power set to 2s, and F consists of 2 to 6, which is how much? 64 events, yeah? Which I'm not going to write down, but I encourage you to do that. So you might want to write down all 64 events. Some of them are going to be simple, but some will be composite. Okay? And you ought to be patient and attentive. When you get all 64, you should make sure that nothing is repeated and that you didn't miss anything. That's actually the way to build your intuition on such topics. Clear? Okay. I know it requires time, but you need to learn this stuff. And there is a very good reason why this course is needed for your statistics specialist degree. Okay? B52 is not sufficient. It's not very rigorous. Okay? Now, for every event A from 2 to s, probability of A is going to be its cardinality divided by 6, because this is the discrete uniform probability model. And then, of course, we could consider a couple of events and find probability of union, etc. I don't want to erase the start of example 1, but I believe it would be quite appropriate to erase this discussion of example 2 from lecture 4. Okay? And you'll have it in the lecture notes. My lecture notes, although they're rough, they're actually working notes, but they're closely related to the videos. Yes. So. Yeah.
Is that the cardinality of A over 64 or 6?
No. 6. There are 6 elementary outcomes here. 64 takes into account simple as well as composite events, including the whole sample space, but it also takes into account the impossible event. Okay? But it's a good point. It's a common error. Not for everyone, but for a certain percentage of students. Okay? Okay. So I consider A, so event A is to roll an even number. And the composition of A is 2, 4, or 6. And event B is to roll an odd number, which is less than 4. So, and the composition of B is just the set of 1 and 3. So this is the discrete uniform model. Hence, P of A is 3, 6, or 1/2. P of B is 2 over 6, or 1/3. Yeah? But what about probability of A cup B? So these events are disjoint, yeah? And since the events are disjoint, then by finite additivity, which I proved starting from the countable additivity, I obtained that it's P of A plus P of B, which is 5 over 6. And this is consistent with this formula that you learned in B52. So this formula was derived by using the sample point method applicable to discrete uniform models. Okay? So these are just simple examples that should help you review B52 stuff and also connect random variables. Say you might be interested in the total being an even number when you roll 2 dice, like if you have 2 rolls, or if you have 2 distinguishable but still balanced dice. Yeah, so many things are possible. Okay? Questions? So, of course, these 2 results are consistent because the cardinality of A cap B is 5. Okay, and now I want to talk about Borel sigma field on the unit interval. So. Okay, now let's take a look at this probability triple, which is our ultimate goal. You do remember that we tried to use the largest sigma algebra, or sigma field, which is the power set of the unit interval, and learn that it's not going to work that well. The power set becomes too big, but we want the probability measure here associated with the continuous uniform U01 distribution from star B52. Okay. So we need this sigma field that is going to be natural for us to consider, and members of such a sigma field are going to be events for our continuous uniform 01 model. Understood? This is a very important distribution for which we often use pseudo-random number generators to produce sequences of uniform 01 numbers used in stochastic modeling. Okay? And there is a particular reason why this distribution is considered separately. I'm going to talk about it later on, hopefully today. Yeah. So we need this second part of our probability triple, script B1. So it should contain, like it's really from star B52, yes, so it should contain closed intervals. So A is greater than or equal to 0, less than or equal to B, and B is less than or equal to 1. Of course, we can consider B to be greater than 1, but this is not going to be useful because we know that probability to be greater than 1 or less than 0 are zeros. Yeah? So we really are interested in these numbers. Yeah? So for closed interval, for half-closed interval, say for a singleton, so these are all intervals. So what actually happens is that such sigma field should contain such intervals, including singletons. It should also contain countable unions of intervals. The complements of countable intersections of countable unions etc. So what we are going to do is to define set script capital G, which all intervals contained in 0, 1, and by intervals I recognize such things. And then I consider sigma field generated by this set G. So it's a sigma field generated by set script G, which is the smallest sigma field containing all such intervals. G. So it contains all the sets from G. So, and it should be closed under complement, countable unions, and countable intersections. Okay, that's how I define Borel sigma field on the unit interval. I'll later talk about such sigma field on the whole real line. Okay? And I don't get into proofs. Of course, we need to consider countable unions of intervals, countable intersections, etc. So I'll give you some examples in the due course, hopefully in a few minutes. But that's how this right sigma field on the unit interval is described. So it's a very natural thing to consider. So, and our probability P, or our uniform probability here is actually has a special name. It's called Lebesgue measure on the unit interval. And I recognize that although French is an official language of Ontario and Canada, so some of you don't know it too well. Okay, so therefore it might be a challenge to pronounce some French names, but this is a contribution of Henri Lebesgue. So you certainly here another related concept for which there are two names used of Lebesgue and Stiltsies. So I somehow studied various languages. I have a tendency to pronounce names of scholars and how these names are pronounced in their original languages. So not always the same as in English. Okay? But that's what this uniform probability measure on 0, 1 is. It's Lebesgue measure. And you know that there are subsets of 0, 1 for which it's not possible to define probability that is going to satisfy all Kolmogorov axioms. Therefore, we need to have some constraints. For such a sigma field, everything works well. Okay? So these are the results which go back to the very beginning of 20th century. Henri Lebesgue was an analyst. He wasn't a probabilist. Okay? So, but Louis Bachelier, whose name you might have heard, who really conceived financial mathematics and the theory of pricing stock options at about the same time, yes. So he was a probabilist, and he even wrote a textbook in probability theory, which was published in 1912, I believe, and whose translation Gerstein Library has in downtown. Okay? But this is the stuff from analysis which became extremely useful in probability theory and stochastic processes. In the lecture notes of last fall, Professor Evans took his time to get into details of building Lebesgue measure, limits, etc. So instead, actually, I don't get into these technicalities. So instead, I provide more intuition and properties of such Lebesgue measure. Okay? So I'd say my approach is more intuitive. You can read technicalities in Billingsley's book or in numerous other sources, which I'm also going to mention. By the way, the book by Gnidenko, and you have access to his book through the library, so it has a lot of intuition, but English translation could have been more polished, unfortunately. So now, I still want this chalkboard available instead of rewriting this stuff again at the end. So I'm going to close this. Okay. Okay. So next, I want to talk about Borel sigma field, script B on the whole real line, which is going to be extremely important for our probabilities measures on R1 induced by random variable x considered here. For this probability measures on R1, we will need Borel sigma fields on R1. Okay? So it is the sigma field generated by the open sets of R1. So therefore, it contains all open sets all closed sets. All unions of open sets, all unions of closed sets, all intersections so I mean countable intersections of closed sets and all intersections or all countable of open sets. it's not the probability. And by the way, so I'll return to it in a moment. So here I said it, and it's going to be relevant to Lebesgue measure on real line. But I already said that it is Lebesgue measure, or it's like a kind of uniform probability associated with continuous uniform 0, 1 random variable. So it's a generalization of the length of an interval. So if your set is an interval, lambda of, say, closed interval AB is B minus A. So, I'll write it. Yeah, I don't want you to stand. So lambda of AB, which is this uniform probability P of AB, is simply B minus A. So it's a natural generalization of the length. So on unit interval, it's somewhat easier, yeah? But then we move from the unit interval to the whole real line. Okay? By the way, when you take photos, send copies to me, please. I ask you to do that. Okay? Is it clear? So for nice sets, it's just the length. Yes, so when you have the union of two intervals which are disjoint, the Lebesgue measure of the union of two disjoint intervals is going to be the sum of their lengths. I don't get into details of this construction. They are widely available. For me, it's more important to describe how it works, to make it easy for you to retrieve and understand all the technicalities, okay? So now I return to what I started discussing about R1, yeah? But we just discussed Borel sigma field, and do you all know what, or I hope you remember what an open set means, yes? So the set in R1 is open if it contains a neighborhood for each point from such an open set. So for each open set that has numerous points, for each point it should contain a neighborhood of each point from the open sets. But it's quite well-known concept, yeah? Okay, so therefore, we should get it like that. But for open sets, we actually have an important theorem, one from set theory, that if certain set E from R1 is open, then there exist at most countably many disjoint open intervals ij, so j is 1, 2, etc. So it's at most countable, which means it could be finite or countable set of disjoint open intervals. And we get the result that our generic open set from R1 is simply the countable union of such disjoint open intervals. So every open set on R1 can be represented as a finite or countable union of open intervals. Okay? So enclosed sets are actually complements to open sets. But what is remarkable is that we don't really need to deal with all open sets. So it's actually useful to figure out the minimal collection of sets which would be the building blocks of our Borel sigma field on R1. And what actually happens is that it suffices to consider only the intervals of the form from negative infinity to a certain point A. And this would be our second theorem. So this Borel sigma field on R1 is generated by the intervals of the form from negative infinity to A, where A is contained in the interval, and A is a rational number. Okay? So other points can be approached by dealing with countable unions and intersections of intervals where the endpoints are rational. Okay? So I just want to consider an illustration. So we have interval AB, where B is greater than A. So A is greater than negative infinity, B is less than positive infinity, and B and A both belong to the set of rational numbers. So this is the set of rational numbers. That's how it's denoted in set theory or mathematics in general. Yeah. So what we actually could do, say, we start from such intervals. Yeah. but from negative infinity to a, where a is included, but say if you want to generate open intervals, then this would be the countable union of such open intervals from an to bn, where an is a plus 1 over n and bn is b minus 1 over n. So for sufficiently large n, yes, so we want an and bn to be both between a and b, so therefore n should be sufficiently large. Okay, so but still we have here open intervals, but this could be written as the countable union from 1 to infinity of the following intersection of these building blocks from negative infinity to bn, where bn is contained, cap for intersection, the complement of the following event from the building block from negative infinity to an, where an is included, but then we need to consider the complement to this interval. Okay? That's how the events from the building blocks can be used to generate, say, open intervals. And we could do it for other things as well. Okay. And I really need to move on. Now, this is the Borel sigma field on R1. And I still have Borel sigma field on the unit interval available. So that's how we defined it. But in fact, Borel sigma field on 0, 1 can be regarded as a restriction of the Borel sigma field on the whole real line. So we just take into account those Borel events from the real line which belong to the unit interval 0, 1. And we get the same thing. Of course, this is all to be proved, but I hope that it makes sense to you. Okay? It is also obtained as a restriction of B on the unit interval 0, 1, which is rather hard, or rather I would say difficult, I would say, technical result. But this sigma field B1 is not a sigma, or is not a sub sigma field of B, because the underlying sample spaces are different. Is the point clear? So we just choose particular events from script B, which belongs to the unit interval, and then we derive a subset of B. And then we look at its members, and we actually recognize that this is exactly the totality of the Borel sigma field on the unit interval. But it's not a sub-sigma field of B. The underlying sample spaces are different. For B1, it is the unit interval. For B, this is the whole real line. And then I want to say a few words about Rn. So when we consider Rn, or the Euclidean space of dimension n, then we get the Borel sigma field script B to n. And Rn, of course, is the direct product of R1 taking n times, and say we have intervals ik from ak to bk, where k is between 1 and n, and it's a kind of n-dimensional rectangle, which we denote by I. It's the direct product of I1, I2, etc., In. Then the Borel sigma field Bn is the smallest sigma field which contains all such n-dimensional rectangles. Of course, you need to consider countable unions and get natural properties. So if in the case where n equals 2, it's a natural generalization of the concept of the area. So in the case where n equals 3, you get the natural generalization of the concept of the volume. Yes?
Is the cross product of R also direct product?
Hmm?
Is the cross product of R also
It's a direct product in n dimension. Like you consider, first of all, it's hard to hear when you wear a mask, of course. Yeah, and we don't have the luxury of.
That's a different notation of R.
So we're here, or so here.
Yeah. Yeah, I just wonder why the partial products of i's are constant. Since Professor mentioned both of the i's and the r's are direct products.
So here it's a direct product. Oh, yeah, oh, I see. I can make a circle if you want, okay? So this is the direct product. So when I use this character times, it's a direct product, okay? It's the same thing. Okay, and now I can erase this stuff. So, so the Lebesgue measure lambda for such I is going to be the product of the length of I1 times I2 times etc. times In, which is a generalization of the concepts of the area and the volume in the dimension 2 and 3 respectively. So then it has the sigma additivity property, lambda of A, so for each Borel set B from script B in, lambda of B is non-negative. It can be 0. Believe me or not, lambda, or Lebesgue measure of counter set, is 0. It has the cardinality continuum, but its length is 0. Yeah. Pardon? No, I is not an indicator function. I is just such a half open, half closed interval. And I is just this half closed, half open intervals, like it's an interval. It's a kind of rectangle in n dimension. Okay? Ik is just an interval in a particular dimension. Yeah.
So lambda would be a real number?
Lambda is a non-negative real number. Okay? I'm just giving you some intuition behind Lebesgue measure. Okay? So for counter set, its Lebesgue measure is 0. So its length is 0, although its cardinality is continuum. So there are other such interesting sets. One of them is Liouville set. Okay? So I should say that each Borel set is Lebesgue measurable, but there is a concept of null set. So, but if A is Borel So if A is a Borel set, and lambda of A is 0, so it's a null set, then each subset is also Lebesgue measurable. So say if B belongs to A, then B is also Lebesgue measurable, and lambda of B, of course, should be equal to 0. So it's a subset of a null set, should be measurable with 0 Lebesgue measure. There are other interesting properties of Lebesgue measure discussed in Billingsley's book, in particular in section 12 therein. There are other numerous sources of information about Lebesgue measure, but I don't really teach Lebesgue measure in this course. Okay? Now, I want to discuss, as I promised, this stuff, which is still present from the very beginning. We return to random variables on R1. Okay? So fix argument x from R1 and consider Borel set B, which is such an interval from negative infinity to x, where x is fixed and included. What is probability that x belongs to the set B? So we just plug it in. So it means that x is between negative infinity and little x, which is included, or it's the same as probability that capital X is less than or equal to little x, or this is the CDF, capital F sub x of little x. And that's what you were supposed to learn about in star B52. Of course, it was easier to employ the probability mass function or the probability density function. Unfortunately, they do not always exist, as you already learned in my lecture number 1. I should also say that if B is, say, an interval from A to B, so then probability that X is between A and B is the CDF f sub x of B minus the CDF f sub x of A. And if we follow along these lines, we obtain what is known as the Lebesgue Stiltsiez probability measure on R1 induced by random variable capital X. So Stiltsiez was a Dutch mathematician. I believe he lived in Leiden, the Netherlands. Okay, so we get a Lebesgue-Stiltsiez probability measure on R1. What happens is that Lebesgue-Stiltsiez measure is actually defined for functions capital F of X being of bounded variation, which is, of course, always the case for each cumulative distribution function considered in this course. Okay, so again, it's a concept from analysis which happened to be extremely useful in probability theory. But that's how we get a new probability measure on R1, which is basically your cumulative distribution function from B52. And because of that, now I no longer need it, because that's how this stuff is related. So I may now erase it at the very end. Now, what we will consider later on is how to find expectation and variance. So Ex and variance of X. So they're going to be integrals from, technically speaking, negative to positive infinity of X df of X. So, and variance is, so expectation will be often denoted by Greek letter mu. Variance is integral from negative to positive infinity of X minus mu squared, or it could be X squared df of X minus integral from negative to positive infinity of X df of X squared. Okay, so of course this should be non-negative. And these are the Lebesgue-Stiltsiez integrals. So in general, in probability theory, these are the Lebesgue-Stiltsiez integrals of analysis. So the examples of Lebesgue integral of analysis. So Billingsley just calls it Stiltsiez integral. And it's in chapter 3, section 17 of Billingsley's. So it kills numerous birds with one stone, because such integral of x df of x, for instance, it will be integral from negative to positive infinity of x times capital F prime of x dx, in the absolutely continuous case, it will be written as the sum over x of x times p of x in the discrete case. So it's going to be something else in this continuous singular case pertaining to Cantor distribution. But that's the mathematically rigorous approach to connect all these things. And the other thing that I want to mention, which you also be expected to learn in star B52, is that if you have continuous, or if you have absolutely continuous random variable capital X, then if you consider its CDF, capital F sub capital X sub little x, this is a new random variable when we plug in random variable as an argument. And this is always going to be uniform 0, 1 random variable, which you be expected to learn in B52. And this invariance result helps us translate everything to the unit interval, and hence replace our Lebesgue-Stiltiès measure on R1 with just a Lebesgue measure on the unit interval. So this transformation is extremely useful, and we can transfer back from 0, 1 to the whole real line, because this function is strictly increasing, and therefore its inverse does exist. And if you consider several random variables together, so we get joint cumulative distribution functions. Eventually, we could get the mixed partial derivatives to get joint probability density functions, and so on. But then new phenomena, such as dependence, are going to occur and be addressed. Thank you, and I will see you next Monday.